I want to talk about discussions about architectures, and in particular, analog architecture concepts, and in particular, talking about architecture with an analog to digital converters. Now, analog to digital converters are one of the few things classically that we often get into sort of architecture theory with analog structures, but we're really kind of loose about it. And so I want to kind of bring in some of these conversations that we often see and things that actually are understood from sort of well-known digital architectures, but also bringing in things that we're starting to understand about analog architectures and pull the things together. And a couple things come to mind. The first thing is when you talk about typical digital computing, one of the things that you notice is that we typically talk about what is typically a large processor model. And so we often will say, well, the processors matter and communication doesn't. The wire length, the communication of the memory, well, that's just kind of a small thing and it just kind of happens. And there are certain discussions that happen in that in sort of classical architectures, right? Where you talk about, as a result, I can say, well, sorting is an n log n problem, right? I can talk about all sorts of things. And there's this order notation. And this is one of the places where this shows up in the conversation. All right, so if we want to talk about, ADCs, well, first thing we want to talk about is we're going to have n bits, which means I'm going to have 2 to the n levels. I'm going to call that with a capital N, so that gives you the exponential term. And so then you end up saying, okay, now I'm going to often do things like count the number of comparators and the amount of delay or the number of times I have to go through comparators in some period of time. And that's typically how we would talk about architectures. All right, well, let's think about this for what is arguably sort of the most straightforward of all ADC architectures, a flash ADC. It's a flash ADC because you say I'm going to take a whole bunch of comparators, basically one between almost every single of the two, every one of the capital N levels, actually capital N minus 1, turns out is what you need. And I'm basically going to take the input and compare it against a known set of references that give me, a choice between one or the other. I save that in a register. I will do some encoding function, and out it goes. Well, normally we'll say, well, the comparators are the big issue here, right? Well, it turns out how many comparators do I need? Well, it's basically order big N because that's how many I have. And you say, well, what's the delay? Well, the delay is every comparator goes at the same time, so the delay is order 1, right? And so you think, okay, that's great. Nothing else to say about the conversations. Except here's a problem that often shows up in real architectures and does show up in digital architectures, but people sweep it under the rug. They'll talk about it occasionally. The computing is maybe not as efficient. And one of the things you find when you start to do analog kinds of things is you start finding that the computation is actually pretty small relative to the computing or to the communication, not because the analog computing is not significant. It just turns out that you've actually reduced a lot of that complexity down, and what's left over is the communication types of questions. So when you actually practically make a flash ADC, and again, this would be whether it's practical or not, but practically, you're going to take your input and you typically will take the input into some sort of a tree structure. Now, that you do this because you want to make sure that the delay from the input to all the comparators is the same. And this is really rather important in terms of how you put that together. Here's the fun part, though. If you start to say, well, how long is the line here? Well, the line I have here is now order between every single one is basically order n, big N. So that means there's going to be a delay of order large N because of the capacitance. Now somebody might say, well, wait, I could route this as an H tree or something like that, but what then will eventually happen is we can have some other routing on the back end. You can do H trees to kind of help some of this on the front end if you're clever, but you can never do both, typically. You can't do an H tree in and H tree out and hope for, and because they're different, you're in trouble. And so what you're going to have here is an order and delay. And in fact, those who build very high-speed flash ADCs understand that this is actually a non-negligible problem in your design. And so this is one of the things you run into. And then, of course, usually you transfer it into the register. There's also some sort of encoding structure that also has some similar aspects, but that's a little more digital, so maybe it's a little bit easier. But what you find when you start actually doing the architectures is that this order 1 delay turns out to be order n, and the order or an order small amount of n in other architectures often starts to go to an order n delay. And so this starts causing all sorts of interesting questions of how to really think about it, right? And so with most of the techniques that you get, when you talk about slow and medium and fast, and they typically span these approaches, where slow is you typically talk about ramped converters, right? And there you say, I'm going to basically do order n comparisons in series because I'm running a ramp and compare it against every one of them. But the areas only have one thing, and so on. And so power, I have to kind of run it for some period of time. For the flash, it looks the opposite, where it's order 1, but the area is order n, and I'm having to still run a bunch of things there. You think, okay, that's great. But if you actually then look at this with the communication delay, what you realize is that this comparison's not so nice. Both of them don't go very well on either metric, actually, in how they scale. And there's some interesting questions and trade-offs to think about here. Like, what is the speed of a comparison versus the speed of a most significant bit, or basically a voltage divider by 2 for a single flip-flop? And you're like, well, those are actually kind of similar. Or delay piece versus that. And you start to go, interesting how you could get into the details of the architecture. Then you also have these medium speed ones, which are typically successive approximation converters, where you use a DAC and you basically build lots of digital logic and compare against it. Or you have an algorithmic converter, which then also feeds into the pipeline stages, which have sort of both a normal latency and a pipeline latency. But if you look at where this is a case of you're kind of algorithmically kind of building and dividing by 2 and adjusting as you have ones and zeros. Both of these are interesting techniques. But even at that, what you start to find is that the cost of mismatch starts to cause trouble here very quickly because of the routing kind of complexities you run into. One way around this is actually if you can get rid of some of the mismatch and some of the complexities for the mismatch aspects in the medium speed converters. For the particularly, say, floating gate approaches is one way to approach that. All of a sudden, these metrics don't scale so poorly even with the communication issues, both in the algorithmic case and in the successive approximation case. And there's some similarities and some crossover there. But it's really important to kind of get a sense of just how much sort of the architecture questions, as well as then sort of what looks like second order issues, but the second order issues can quickly dominate everything in your architectures. And so this is what makes it fun when you do analog to digital converter design, because you really get to do some architectures. And by the way, this is not an issue just in analog to digital converters, but as things expand to more and more computing on the analog side, you begin to realize all of these architecture questions show up again and again and again in many of these different problems.